Okay, welcome back. In this video, we'll be talking about normal distributions. And so, to start with, let's talk about what the word normal means. So, what does this word mean? Well, in the English language, or English speakers in general, we use this in everyday conversation fairly often, I would say. And I apologize, my throat is very hoarse today, for whatever reason. But anyway, so in English, we use this word pretty frequently. Like, for example, you might hear someone talk about the weather, like, oh, this is pretty normal weather. This is pretty normal amount of snowfall for this time of year. If you've ever eaten some food that tastes pretty weird, you might get this sudden urge to check the expiration date because it does not taste normal, which might be concerning. I remember back in school, for goofing off in class, talking to your friends, passing a note or something. Then all of a sudden the teacher's looking over. It's like, shh, the teacher's looking. Act normal, act normal, right? Or yeah, just talking to some friends who might say, yeah, I had a pretty normal weekend. Didn't really do much, right? So this is a word that we use pretty often, and generally we're referring to things that are typical. And in social science, it's quite similar, right? We're saying typical, or I suppose more accurately, we're saying most frequent. But one example coming from an article I found online about birth weight. Um, so finding that low birth weight babies are at higher risk for mental health problems later in life. And so this was a quote. This was I think, a press article written by the authors of the study. But they said that their findings provide evidence that individuals born at extremely low birth weight are at higher overall risk for psychological difficulties than their normal birth weight peers. Right. And so we're talking about normal. What we're really referring to, although we're using it to mean typical or most frequent, we're technically using a statistical term to refer to the statistical norm. And in the world of social science, and especially in the world of psychology, there's a lot of, I'd say, discussion about the use of the word normal. Um, just for example, I used to work with children ages 6 to 21 with various developmental disabilities, and we were actively told not to use the word normal when referring to kids that don't necessarily have developmental difficulties or disabilities. And so this is a whole discussion we can have. I'll have another video that goes more in depth on the use of the word normal in our field and in social science more broadly. So do watch that, and just know that, yeah, if this is a loaded word, or if you've heard some of the controversy around this word, we'll talk about it in another video. But in the stats class, this video is going to stick to the statistical concept of the norm. And so the statistical norm is generally referring to what is most frequent in a normal distribution, or really in any distribution, but in a normal distribution, it's a very particular type of distribution. And we'll talk more about its characteristics here in some upcoming slides. But was that last module? I think it was the last module we talked about standard deviations. And so in this example of a perfectly normal distribution, you can see that we have our population mean and then proportions or percentages of the overall sample within these different sections of the distribution. And those sections are divided by standard deviations, right? So here on the right of the mean, we have this is 34% of the sample falling um, within one standard deviation above the mean, and another 34% are in one standard deviation below the mean, right? So that means roughly 68% of values fall within plus or minus one standard deviation of the mean, right? That's a characteristic of a normal distribution. Then you can see further proportions. The point is, if oh, what's a good example here? Say this was a distribution of height, right? Like, I don't actually know what the shortest and tallest adult humans are. Um, yeah, I would hesitate to guess. But if this is adult human height, right? We'll say at age 25, right? Then we would have our mean here, and it means that most people fall on average or within one or within plus or minus one standard deviation of that height. And we have very, very few people who are like 8 foot tall, and very, very few people who are like, I don't know, 3 feet tall, right? Most people are in the middle. right? And that's what we're referring to when we talk about the norm and normal distributions. And so this, I think this is supposed to be animated. No, maybe that's a different one. Um, but yeah, just another example of this. So in this one, it's showing the individual standard deviation proportions. This is showing the combined plus and minus. So 68% within plus or minus 1, just over 95% within plus or minus 2, and 99.73% within plus or minus 3 standard deviations. And when we're talking about normal distributions, the reason these are significant in statistics, well, really, there's a lot of reasons, and we'll come back to that in this video and in other videos. But when we're collecting quote unquote real world data about human behavior, societies, right, whatever it may be, oftentimes it's going to approximate a normal distribution. And so this is a GIF that I found online that just goes to show an example. And so you can see that the distributions are changing, right? The actual bars in this bar graph. And as they change, you can see we're cycling through different sample numbers, right? And so this represents height, and these are just different samples of height, right? The distributions. And so you can see most people in these samples were between 170 and 180 centimeters. I forget how many feet and inches that would be for us American folks. But you can see like the distributions do change, but generally speaking, they all sort of approximate to a normal distribution. And that's a characteristic we'll come back to when we talk about the central limit theorem. But just important to mention right now that although we might collect data that doesn't look normal, if we collect more data, oftentimes we will find a normal distribution. Most human traits, for example, if we measure them and we get enough individuals, we'll find a normal distribution in the data. And so to talk more about the characteristics of these distributions, so yeah, it's mathematically defined via the mean, via standard deviations. It's theoretical, right? Rarely do we find a perfectly normal distribution in actual data, but they approximate to this normal distribution. And it's symmetrical, right? So a perfect bell curve there. And if you remember when we talked about skew, the mean, median, and mode are all on the 50th percentile in a normal distribution, right? So mean, median, and mode are all overlapping in that center of the symmetrical distribution. And the mean can equal any value, right? It doesn't have to be one specific thing like 0. It can be really anything, right? You could have a normal distribution at a mean of 10,842.67. I don't know why that number came to mind, but it did, right? So the mean can be anything. Standard deviations can equal any positive value, right? So it's theoretical, and we're really not limited to the mean and standard deviation as long as they follow the rules of distributions in general. And in this, the area under the curve is equal to 1, or in other words, 100%. And then each section here represents a proportion or percent of the overall sample. So again, that's how we got 68% within plus or minus 1 standard deviation. And then if we add all of them up, we'll get to 1 or 100%. And the tails are asymptotic, I think is how you pronounce it. But again, theoretical, and means that these tails never actually touch the x-axis, right? They just kind of continue. And you'll notice all the computer-generated images will look like that. I believe the ones that I hand drew do touch the x-axis, so I apologize. I'm just not a good artist. Okay, and so the standard normal distribution is a distribution that we'll come back to, and I'll explain more for why this exists in a second. But this standard normal distribution, we just said that a normal distribution can have any mean. This is just one specific normal distribution. We call this standard normal distribution, or you might think like standardized normal distribution, with mean equals 0 and standard deviation equal 1. And so you can see this here. And those standard deviations in the standard normal distribution are z-scores, or what we refer to as z-scores. And so these z-scores then are values on the x-axis of a standard normal distribution. And so again, when you hear standard normal distribution, just think standardized, right? Like this is what we kind of go back to inform um, our analyses and interpretations, right? And so in this standard normal distribution, we have these z-scores. You've probably come across these before if you've taken stats in any sort of capacity. And even if not, I feel like you might have heard of these in some kind of math class. Um, and so, yeah, basically stating what I just said, the z-score specifies the distance or the number of standard deviations of a value from the mean, right? So if our mean is 0 and we have a score of 2, guess what? That is 2 standard deviations above the mean in this standard normal distribution. Yeah, and so here's another GIF to animate this. And so as we cycle through these standard deviations, you'll see that the tails, the area in the tails, get smaller and smaller, right? Because again, it's just um, proportionally counter to whatever is within the shaded area here. And so to argue, or to, I guess, provide some context for why we need a standard normal distribution and why we need z-scores, because that's a question I often had when I was learning about this. So let's imagine that we're looking at temperature records, and for some reason you find that the person recording the records was, I don't know, either very, very random or very, very sadistic and wanted to make your life challenging. And so you find 78 degrees Fahrenheit. Again, if you're an American like me, then that's easy to understand. 22 degrees Celsius. Okay, I've encountered Celsius. I couldn't do the conversion off the top of my head, but that might mean something. That's above freezing. 301 Kelvin. Okay, now I officially have no clue what we're working with. That could be absolutely frigid cold, or it could be boiling hot. I honestly have no idea because chemistry was a long time ago. And so how do you make sense of these data, right? Well, the key is to convert things, right? To do conversions. And in this case, we need to find some sort of standard that we can compare everything to. In this case, our standard is just going to be one of the systems for temperature. I'll choose Fahrenheit because that's what I know. And so if we convert these, okay, now I have some sense. So 22 Celsius is less than 78 Fahrenheit. 301 Kelvin is more than either of those two. If I had to pick one temperature, I'd probably pick this one, right? Yeah, 71.6, I think. 78 is starting to get too hot for me. Right, and so point is, we need to convert things sometimes to um, or compare in any sort of meaningful way. And the same is true with distributions, right? And that's why we have the standard normal distribution and z-scores. And so we have that standardized sort of measurement or system to look back to interpret things and make comparisons. And so, yeah, so to basically reiterate that more explicitly, so normal distributions, like we said, are theoretical. Real world data distributions are rarely identical. So for example, I just use a simulator to kick out some distributions, and you can see they generally, like, you can follow a curve if you wanted to draw one on there, but they don't look exactly the same, right? There are some differences. So in order to practically compare distributions, we need some sort of standard theoretical, I guess, quote unquote, perfect or symmetrical distribution to look back to. And that is the standard normal distribution. And there are a few different ways we can use this to inform things. And this week we'll be talking about z-scores. We'll also talk about t-scores in upcoming modules. And that's something that, again, if you've taken sets, you might have come across before. And so when we use this distribution, if we're taking some sort of imperfect real world data, we can convert it to a normal distribution using a standard normal transformation. So in other words, we can take these imperfect distributions and transform them to a standard normal distribution for the sake of interpreting our information. And so we have two formulas with which we can do this. One for population, one for sample. Um, so yeah, again, X here means score or value on whatever the scale is that we were working with. Like if it was temperature, the X would be the temperature value, so on and so forth. Mu or M is the mean for the population of the sample. And then, gosh, I should really look this up. Sigma, God, yeah, I should look it up. this symbol and standard deviation referring to the variance, right? Either as variance or as the square root of the variance, the standard deviation. And so here, if you want to pause it, get the equations without all that noise. So let's do an example to depict what we mean by this. So let's see. So this is an example coming from the Prove It Terror textbook. So a researcher measures the farthest distance in feet that students move from a podium during a class presentation. So in other words, we have students, they have to give some presentation in class, and maybe we want to see if people move around very much. And so we measure the furthest people move, and then we measure how many feet that was away from the podium, and we get a distribution. And we find a normal distribution with a mean of 12 and a standard deviation of 2. Right, so on average 12 feet, 68% were within, what would that be, 10 and 14 feet. And so here, let's see, what is the z-score for x equal 14 feet? So in other words, we have our distribution, and we can see our mean is 12. We have standard deviations of 2. And so we want to know the z-score for a value of 14. And if you were paying attention earlier, you might already know the answer. But to show how we get there, we'll plug it into our equation from the previous slide. Z equals x minus m over SD. So we'll plug in our x of 14. We'll plug in our mean. We'll plug in our standard deviation. That's going to reduce to 2 over 2, which equals 1. So in other words, 14 is plus 1 standard deviation above the mean. That's what our z-score indicates, right? Our x value of 14 is 1 standard deviation above the mean, as indicated by its z-score of 1 in this transformation. Okay, cool. So you might say, okay, what's the point? So at this point, yeah, we were able to do this, but what else can we do besides just know how many standard deviations we are away? Because we could just do that math like in a different way. And so there is a point to this. We can use it to identify and do several things. Before we get to how we do that, we need to talk about the unit normal table, because that's something that we will use to identify things. So this in the Prove It Terror textbook is Appendix C1. If you don't have your text handy and you Google for this online, note that the textbook does some things slightly different with this table, and I'll talk about what they do different here. So this is a screenshot from your text, from what that table looks like. So in this, it includes a list of z-scores, one column, column A, corresponding probabilities or proportions associated with each z-score, and column B and column C. And to interpret what these columns refer to, so what did I just say? Column A is positive z-scores. For negative, it's just the inverse. So if we had a z-score of 0.10 and we wanted to actually look up a z-score of minus 0.10, we would just do the inverse. This would be negative, 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 and we can interpret it similarly. Or actually, no, I apologize. This would be negative, but these would be the same, right? Because they're referring to proportions. So those values would still say positive. Yeah, and so to graphically depict this, because I don't think they did a good job at depicting it, I drew this out. And so you can see here we have our mean. Column A is the z-score, right? Column B is the area between the mean and the z, and column C is the area beyond z in the tail. And so this is just an example. I did this with a z of 1 because I wanted to draw a straight line, and I had a line to guide me. But for any z-score, when we look it up, what we're finding is essentially that value on the z-axis here, the horizontal axis for the z-score. And then column B is going to tell us whatever the area is between the mean, in this case 0, and that z-score. And then column C is telling us whatever comes on the right side of that. Because again, this is just looking at positive ones. Negative would basically be the flipped version of this image. So z-score would be over here, and we'd have column B and column C. And so there's all this in one place if you want to use this as a resource. And again, I mentioned that your textbook, your textbook does some things different than if you Google online. just pay attention to what the areas represent. Because in here, the main thing here I'd say is column B, in that we're looking at the distance or the area between the mean and Z, and a lot of them just look at Z and then everything on the right and everything on the left. So this B value will probably be different in some tables, and just know that's because it's looking at the whole proportion to the left of the Z-score, not what's left of the Z-score, but right of the mean. So yeah, just let me know if you have questions on that. And so we can use this table to identify several things. We can identify proportion or probability for any given score, or we can identify scores that fall within a given proportion or percentile. Steps listed here, I wanted you to have these if you want them as a resource, but I'll walk through these so I won't spend time on them here. So let's do an example of each. First, identifying proportions. So again, pulling some examples from the printed text. So let's say if we have a hypothetical line of research. This is just, yeah, for the sake of example. But say we have research that's shown that chewing gum can improve mean scores on a standardized math test. And I'm sorry, I worded this kind of poorly. Chewing gum can improve your scores on if you're taking a standardized math test. So say you're taking the math portion of the ACT. And you chew gum, you can, according to this research, improve your score by an average of 20 plus or minus 9 points just by chewing gum. Must be some really good gum. So, for example, if your first test score was 20, then on average, people's second test score would be, oh gosh, I'm sorry. If your first test score was X, on average, your second test score would be X plus 20, right? So if your first test score was 60, you could expect to get an 80 on your second test on average, right? But it'd be anywhere within that range because it's a distribution. And so let's find just that. Assuming that these data are normally distributed, what is the probability that a student who chews gum will score between 11 and 29 points higher the second time they take the test? Right. So in other words, we expect it to improve 20 plus or minus 9 points. Okay. And so what's the probability that will land in that range? Okay. So let's just write it out for some housekeeping. M equal 20, ST equal 9. Okay, and we're going to do a z-score transformation for x equal 11. Let's start at the bottom here, the bottom portion of our range, the lower limit. And so we'll plug in our values, and we will find z equals 11 minus 20 over 9, x, m, and standard deviation. We get a value of minus 1, right? And so you can just see that mapped out here. And so we'll see our z-score minus 1. Okay, that's where our 11 is. That makes sense. And then if we do I'm sorry, I'm getting ahead of myself. So let's look at our z-score table for proportions. Now if we look at that, and eventually we'll find an A of 1, and then we'll find this, and what we're looking for is B here, right? Because what we're trying to find is the probability that they'll be in this range, right? Between 11 and 29. And so with 11, we're just looking at this shaded portion right here. I hope you can see my mouse. If not, then this might not make any sense. And so we find that for 11, and again, since this is positive, we're looking at negative, so we just assume this is minus 1, and technically we're looking at this shaded area, but it's still going to be a positive proportion because it's an overall proportion of the total value of 1. So I find p equal 0.3413. Do the same thing for 29, and we'll find a positive 1, p equal the same. And then to find proportion between two scores, we're just going to add their proportions together. In other words, we're adding the area under the curve. And so we'll add those together and get a value of 0.6826. And so in other words, so step 2, we were looking for this area. Step 3, we're looking for this area and the corresponding proportions. And step 4, we just added those two together, right? Added the red here, added the black. And we found p equals 0.6826. In other words, roughly a 68.3% likelihood of scoring between 11 and 29 on the second time taking the test, right? So pretty good odds, or pretty good probability, I should say, after having harped about odds in previous videos. So another way to depict this, coming from your textbook, right? But so this is a simple example because we're making it easy, sticking to z-scores of 1 and -1, but hopefully starting to make some sense about, okay, what we use this for and what kinds of questions we can answer. And so for another example, instead of identifying the proportion, now let's identify a score. So in the general healthy population, IQ scores are normally distributed with a mean of 100 plus or minus 15. Here we're working with population statistics. And I think technically we probably should have been the previous one, but our values were still, yeah, the formula still works the same. And so assuming these data are normally distributed, what is the minimum score needed to be in the top 10% of intelligence scores in this distribution? In other words, let's say our ego is feeling fragile and we want to feel smart, and we're like, you know what would it take to be in the top 10% of IQ scores? Well, let's find out. So it always helps to draw these out to get a sense of what the question is that you're asking and how you can get there, how you can get to your answer. And so if we draw the distribution, um, even without drawing the mean and standard deviation at this point, we just know that we need to find an x value, in other words, an IQ score value, beyond which the tail is 0.1000, right? Because that is, in other words, 10%. So we want to find an x score with a tail that is 10% of the overall proportion. All right, and so if we do this, we look up in our z table, we look up, in this case, p, right? So we're looking up a different column. We're not looking up z, we're looking up, in this case, that would be column C, I believe. Yeah, I'm not going to go back to the picture because that'll screw everything up. But yeah, I believe that we'd be looking for column C here. And we find that, we find a z of 1.28. And so we have our z value now and the standard normal distribution. And so now we need to basically work backwards. We have our z. Now let's go back and find what the x would be. So what x score in the distribution corresponds to that z score? So we can substitute it into our formula. If we know that this is the formula, this becomes an algebra problem. And we know our z of 1.28. We don't know x, we're looking for it. We know our variance, we know our mean. And when we do that, we solve the algebra problem, we end up with an x value of 119.2. Right, so in other words, a score of 109.2 on the IQ test is a cutoff for the lowest score that would place us in the top 10% of this distribution. Or in other words, any scores that are 119.2 or above are considered to be in the top 10%. Right, and so once again, just rehashing our steps, we drew this out. We were trying to find the x value that corresponded with a c of 0.100, and then we worked through these steps to get there. And one thing to look out for here is, yeah, again, just pay attention to well, actually, no, I don't want to get ahead of myself. We'll keep it simple for now. When we get to t-test, we'll have some other considerations, but we'll keep it simple. Just let us know if you have questions on this, and that is actually all we have for this first video. We'll see you in the next one.